Thanks, Chevy, and thanks everyone for being here and staying till lunch. So I know that I'm standing between you and lunch, so I guess what that means is we can just go for much longer, because right? Because who needs lunch anyways? All right. So, but all kidding aside, I'll try to do this in within 40 minutes. All right, so I'm going to first of all talk about this problem from kind of the algorithm design perspective, and then I'll talk about the learning perspective. From the algorithm design perspective, right, which is kind of where I come from, then I think about what I'm going to talk about in the following way. So when we learn how to design algorithms, right, we learn how to solve problems like shortest paths, right, and we're told that we're given some sort of weighted graph, like in this example, and what we're asked to do is we're trying to find like the shortest path or shortest weighted path right, from source to destination, right? And then we learn all these algorithms, right, that basically find this shortest path, right, from this source to destination. Okay. But when we teach these algorithms to our students, then actually the problems that they face in the real world, they actually look very different from this shortest path problem that we teach them how to solve in an undergrad algorithms course. The problems that they face, they look something like this. Okay, so maybe these are some, like intersections, right, on a map from, right, on a map here in Cambridge, right. And basically, what they're asked to do is they're asked to find like the shortest path or the quickest way to get from Harvard to MIT in this case. So when they're faced with these problems, right, there is no weighted graph that's given to them, right? And somehow they have to figure out what is this weighted graph. So a reasonable thing that they would probably do is they would try to somehow learn, right, what like what the weighted graph would be in this case, right, from data, right? And then they would try to use that learning to design an algorithm, right? So maybe they'll kind of come up with some sort of complex model, right, where they come up with a graph, right, where the nodes are the intersections and the edges are the roads, and they're going to try to predict the congestion times, right, from data. And once they have this kind of like this idea of this prediction of a model, right, what they're going to try to do is they'll apply the shortest path algorithm that we taught them how to use, right, and come up with the quickest way to get from in this case from Harvard to MIT. So what they're doing is really they're not given a weighted graph and finding the shortest path. What they're doing is they're taking data, right? They're making some sort of prediction to come up with a model, right? And then once they've made that prediction, then they're applying an algorithm to make that decision. Okay? And we stress out a lot about like epsilons and running times, right? And when we design algorithms, and what we can ask ourselves is what happens when we design algorithms where we're not designing them over a model that's given to us, but actually over a model that's been learned? Okay. Another example is an example about contagion in social networks. So here we have some sort of social. We have a social network, and what we have is we have people that are influencing one another or talking to one another, right? And we model this again as a weighted graph. But here the weights, they're not congestion times, but they're the likelihood of one person forwarding information to another person, okay? And the problem here is basically to identify a subset of people that are most influential in the network, right? So a subset of people such that if we choose them to sort of start spreading a rumor, that rumor will reach as many people in the social network as possible. Does that make sense? So again, what we have is we don't know the model, right? We don't know there's no weighted graph, there's no ground truth. Instead, there's data, right? We use predictions to come up with some sort of model. And after we come up with some sort of model, then we apply an algorithm to come up with a decision on who to select that's most influential. Okay? All right. We can formulate this a little bit more, right? And we can say, well, really what we're seeing is we're seeing samples, right? And this is what we see when we say data, right? We use learning to use these samples to basically come up with some sort of model, right? The model is the kind of a model of our objective function that we're trying to optimize to make a decision, right? And then what we're trying to do is we're trying to basically optimize over this model to come up with some sort of solution. Does that make sense? Okay. All right. Now, the question that we want to ask in this talk is like, can we actually design algorithms that perform well when the input is learned from data, right? Now, from the learning perspective, basically we see that in learning, people study the same kinds of problems exactly, but instead of thinking about them as algorithm design problems where the input is not known, they think about them as learning problems where basically what they're trying to do is instead of trying to make a prediction, they're trying to make a decision. Right? So we see this in kind of a multi-reference alignment. We see this in problems where we're trying to optimize things like data center cooling and in kind of like industrial control, right? If you've seen kind of what DeepMind is doing. And more recently, we've seen like this line of work. I just picked a few about basically optimizing hard optimization problems using deep learning, using reinforcement learning, right? That is all trying to basically come up kind of like with the same objective, right? We see a bunch of data, right? We want to solve an optimization problem. Why go through the trouble of actually designing an algorithm? Let's just design a really good prediction model or really good prediction algorithm that will come up, with the decision itself, right? Does that make sense? So if we want to phrase it, it's exactly the same kind of problem where we have data, right? We could make a prediction to learn a model, but our goal is really to make a decision. And here, like the motivating question is, can we actually design learning models that produce desirable results, right, for optimization problems? Does that make sense? Okay. So this is the kind of problem that I want to talk about, and I want to formulate. I want to kind of basically what I'll do is I'll give some sort of formal model that we can actually start asking questions about this problem. We'll give some results, and then we'll see kind of what are the things that we can and can't do in this setting. Okay? All right. So what I'll do is to have this discussion, I'll use two models. I'll use some modular functions, and then I'll use also convex functions. Most of you guys probably know convex functions. Maybe less of you probably know some modular functions. So I'll just give you like 2 slides about some modular functions, right? And then we can have this conversation about some modular functions, convex functions, and we'll see why some modular functions are actually kind of a pretty good model to study this kind of question in this case. Okay. All right. So very briefly, an objective function f is submodular. Basically, if it has a diminishing returns property. Okay, so what does it mean? So now we're talking about a combinatorial function. It takes elements from a ground set. Okay, and basically what I'm going to say is I'm going to say that this objective function is submodular if whenever I add an element A to a subset S, I look at the marginal contribution of that element. This is f of S union A minus f of S is greater or equal to the marginal contribution of adding A to T whenever A is a subset of S, whenever S is a subset of T. Let me just give a kind of a quick example with a cover function. So if we look at kind of like if we think about this as an objective function where our objective is to cover as much of the white space, okay, here, right? Then whenever I have a set S of these two disks, okay, whenever I add this disk A, I have a marginal contribution of adding A to S, okay, and that's the marginal contribution. But when this S grows to T, the marginal contribution of A decreases. Okay, so that's a submodular function. So anything that has this property, any objective function that has this property, is a submodular function. Okay, okay, so what's so good about submodular functions? They actually capture a pretty broad range of applications. That, whenever a lot of things in machine learning, a lot of things in game theory. Whenever we want to optimize objectives, submodular functions is a very good model. Okay? But something that's also good about them is that they're basically amenable to optimization. So we can think about like a simple problem like max cover, where we want to select k disks whose total coverage is maximal. Okay? So if we just do a simple greedy algorithm where in each iteration we select the disk that has the largest marginal contribution, right? That algorithm is not going to be optimal, but it will be 1 minus 1 over e of the optimal solution. Getting the optimal solution is actually NP hard, okay? And this 1 minus 1 over e is actually the optimal approximation unless p equals NP, or you can use exponentially many queries. Does that make sense? Right, so we have some modular functions. They model they model anything that has a diminishing return property, right? Pretty broad applications. In terms of optimization problems there, if we want to solve simple optimization problems like maximizing a submodular function under a cardinality constraint, right? Like selecting k elements whose total value is optimal, it's an NP-hard problem, but it's not that bad because we can get a good approximation, 1 minus 1 over e, with a simple greedy algorithm, right? And this algorithm is optimal unless p equals np, or we allow for exponential communication. Okay? So that's the gist of it. So basically what I want to do is I want to use some modular functions as the objectives that I want to optimize, and I want to understand whether it's possible, if I don't know the actual functions that I'm trying to optimize, if I'm learning them, whether it would be possible to actually get to good optimization results. Okay, so the first way I could do this is with the learn and optimize approach. So I can say I have some data that's that allows me to learn a function, whether it's a submodular function or a convex function. What I can then do is I can learn that function, okay? And after I've learned that function, I can make a decision by optimizing over the function that I've learned. And the question is whether this is a good idea or a bad idea, okay? So what I'm going to see is I'm going to observe samples. In the case of a submodular function, I'm going to observe sets and the values of these sets, right? I'm going to use machine learning. I will come to some sort of model, right? I'm going to come to some sort of model, which is, right, a surrogate function. This is f tilde, which is not really f, right? It's an approximation of f, right, because I'm learning, right? And then what I'm going to do is I'm going to try to optimize this, this objective, right, using an optimization algorithm. So whenever we're learning a function, right, basically what we do is we produce some sort of surrogate function that approximates the original function that we actually want to optimize. Okay. So if we actually want to do this learn and optimize paradigm, what it means is it means that we're optimizing over surrogate functions of a submodular function or a convex function. Okay. So what does it mean? So I'm going to say for the submodular case, I'm going to say that f tilde is an epsilon erroneous oracle of f, right? It's a surrogate function. If it approximates f everywhere up to some sort of like small, right, small epsilon approximation. Yeah?
You don't require that f tilde is submodular.
Exactly, I don't. So great question, right? So like, do we require f tilde to be submodular itself? So no, because, right, if it were submodular, then the answer is obvious, right? If it were submodular, then it would be easy, right? Because I know I can optimize the surrogate function. It's close enough to the true function, and I have a good approximation, right? Whenever you're looking at the literature of learning submodular functions, it's always improper learning. They never learn the function that they learn is not a submodular function, but an improper one. And the question, or non-submodular one. And the question is, does this help us in any way? Can we kind of like learn these, learn submodular functions, and then take what it is that we use to learn and then optimize from that. Okay. So the answer is no. And the reason is because it turns out that for submodular functions, whenever there's a small error whenever you're epsilon close to being a submodular function, even if this epsilon is subconstant, then you would need exponentially many queries to get any reasonable approximation. Does that make sense? So you take a simple problem like maximizing a submodular function under a cardinality constraint, okay? If the function is submodular, we know how to solve it like really well, right? But now, if the function is not exactly submodular, right, but it's almost submodular, then what it means is it means that there's no algorithm that you can give me that is guaranteed to give me any reasonable approximation, right, using polynomially many value queries to the function, right? Meaning that if we're learning functions, whenever we're learning them, we're always learning them with some sort of error. And then if we want to optimize over this surrogate function that we've learned, then there are no guarantees that we can have over these algorithms. Does that make sense? Yeah.
Yeah, Does this also rule out approximate submodularity for F tilde?
So, okay, so what does this mean, approximate
Like, let's say
submodularity?
F tilde satisfies the submodularity constraints.
Perfect. So
1 minus epsilon.
exactly, and so right, it does not, right? If F tilde were submodular, then we would be able to, right? If we can approximate F tilde well, if F tilde approximates F well everywhere and it's submodular, then right we can design algorithms. Can we do this, right?
No, but F tilde is approximately submodular, meaning it satisfies the submodularity constraint with
Yes.
the 1 minus epsilon on, let's say, the right hand side.
So if it's approximately submodular like we had in the previous slide,
But there's a 1 minus epsilon on the right hand side of the equation.
and on the left-hand side, or
No, not on the left hand side.
even if it's one-sided, you can show that it's equivalent to the two-sided. But
I'm asking.
no, yeah, no, it's a great question, but yeah, but it doesn't
Doesn't help.
does not help, Okay. Okay, so that's a modular functions, and then the kind of like the whenever presenting this in front of traditional learning people, they're very happy to see this impossibility result because they said, oh, this is because some modular functions is just a bunch of garbage, right? What you should really be doing is optimizing convex functions. That won't happen there. So we showed that that's not the case. Okay, so exactly the same thing happens for convex functions. Okay, and just intuitively, why does this happen? Well, think about your whatever your favorite convex function, and now think that you're like approximating like really well. And just for intuition, suppose that you're just running gradient descent or stochastic gradient descent. Okay, right. So what happens is, you just go somewhere, right, and you get stuck in a local, right, optima, and that's it. Okay. Again, what's kind of like if you want to use convexity as intuition, right? So what's happening here is that whenever we have approximate or surrogates, right, of the original functions, we lose all gradient information. Does that make sense? And then that makes it, hard to optimize these functions. Yeah. Should you restrict the approximation to what? The approximation to be convex. You're saying that the surrogate function should be convex. Yes, exactly. Like that would be the right thing to do, right? But that's not what that's not what people are doing. That's not the requirement, right? That people are doing. I can give you a lot of favors, okay? But right, like so now, right? Like maybe the question should be the following, right? If we had a way of whenever we're learning, right? If we had a way of producing functions that are, convex or the functions are submodular, then we're good, right? Because then we can just optimize, from. So maybe the fact that we haven't seen these learning algorithms is just because, that paper hasn't been written yet, right? Maybe there is a paper that's going to be written about, learning, like kind of like learning some modular functions or learning convex functions everywhere that we can do this. Does that make sense? So we'll get to this in a second. So the reason why why this doesn't work is because these errors are all adversarial, right? I can construct an approximation of a submodular function, right, in a way where these errors are really adversarial, so that it really kind of screws up with my function. What you can ask is like, what happens if these errors are not adversarial, but they're actually some sort of product of noise, right? So there's some sort of this error is not just is not adversarially chosen, but it's actually drawn from some distribution. Okay. So in both cases, I'm saying that the noise is consistent, right? If I query this function multiple times, right, then I'm going to get the same result. It's just that what I'm saying is that the error is just drawn from some distribution, and it's not adversarially chosen. So there, what you can show is you can actually show that you can recover the optimal guarantees for some modular optimization, right? Whenever you have some sort of approximate version of the submodular function, but this approximation is somehow like a result of the distribution from a very broad class of distributions. Okay, so there are cases where you can get approximate some modular functions that work well, right? So now the question is, what happens in the cases that we care about? And these are the cases of learning and optimization. So in order to understand this, right, basically, if we want to understand, if we move from predictions to decisions, then what we don't know is we know that there are some models for which this works, and there are some models for which this doesn't work. We don't know whether we can produce these models for which this works. So the question that we should be asking is, we should just forget about the models, and we should ask a broader question. If I'm given a set of samples, drawn IID from some distribution, as in the learning model, okay? Can I solve an optimization problem from these samples? That's the question. If I want to do this by constructing some sort of submodular or approximate submodular function in the middle, that's fine. I can do whatever I want. But the real question is, right, can we see training samples, do something, and then basically solve optimization problems? Does that make sense? Yeah?
Sorry, so there's not going to be some loophole where I say, if I can do this, then actually implicitly there is a function f tilde in the background that can reconstruct and show that whatever algorithm I used to actually straight up do this is actually optimizing a function f tilde, which was not really trying to get close to this function f, but this is really the function I'm optimizing.
So, well, somehow like we shouldn't, right, like it shouldn't matter in some sense, right? Like whether, right, like, well, if all we care about is, if what we have is we have kind of these samples and data, right, and we want to come up with a solution, it's not going to matter whether there's a way to construct this, right, the surrogate function, or isn't there a way to maybe there's a different algorithm, right? We don't know, right? Does that answer the question?
But
Yeah.
you guys said this is sort of equivalency to like properly learning submodular functions.
To properly learning submodular functions? Well, not necessarily, right? Because we somehow like we don't necessarily need to produce a.
Sure. No, but I guess you're asking whether.
There's a reduced.
Yeah.
Not that I know. Not that I know, at least. Okay. So we can kind of like slightly kind of formulate this more. We can ask, so when is this question interesting, right? We can argue that it's interesting if the function is not statistically learnable, right? PAC or PMAC is what you use for learning submodular functions. If it's not statistically learnable, then you can argue that it's not really interesting because you don't expect this problem to, right? You wouldn't expect this to happen because there's something kind of information theoretically difficult about the objective function. Okay? So let's say that the function is statistically learnable, and let's say that it's amenable to optimization, right? So I'm only going to restrict myself to convex functions or submodular functions. And now I'm asking, is it then possible to optimize functions from samples? And when I say possible, I mean polynomially many samples, right? And like all the arguments of the problem, right? And obtain meaningful guarantees. So my input is a set of samples drawn IID from some distribution, right? My objective is to solve an optimization problem, right? I'm assuming that the function is statistically learnable. It's either PAC or PMAC learnable, and the function is an APX, okay? The objective function, or the kind of solving the optimization problem. Can we then do this? So it turns out that the answer is no. Okay? You can show that there are problems where the objective function is statistically learnable, right? They're amenable to these problems are amenable to optimization, but you wouldn't be able to get any reasonable approximation when you're using polynomially many samples drawn from any distribution. Does that make sense? So what are these problems? So if we want to do this, then this is impossible. Okay? So for example, max cover, like the problem that we talked about in the beginning, right? You can show that for max cover, you can get an approximation better than this if you're observing fewer than exponentially many samples drawn from any distribution. Okay? For more general submodular functions, you can show stronger in approximability, okay, if you're observing fewer than exponentially many samples. Does that make sense? Right, so if you're trying to solve in general, if you're trying to solve a submodular optimization problem, right? In this case, it's a modular maximization problem. Even submodular maximization problems are heavily used in practice, like max cover. The influence in social networks is a generalization of max cover. So if you're trying to solve one of these problems and you don't have the true objective function, but you're learning that objective function from data, then you don't have any guarantees about the outcome that you're producing, unless you've observed exponentially many samples. Does that make sense? So you could be running optimization algorithms all you want, and you can kind of like spend a lot of time stressing about the running time or the approximation guarantees that they produce, but there's just no guarantee to kind of like the quality of the approximation that you're producing. Okay. So you can again sort of be smug and say, okay, so modular maximization, who cares, right? To combinatorial optimization problem, you said it's NP hard in the beginning, so maybe that's a problem. So unfortunately, that's not the problem. You can show the same impossibility result for problems that are NP, like submodular minimization, okay? And you can show exactly the same approximabilities for convex optimization. Okay, so if you have a convex optimization problem, you don't know the objective, you're learning the objective from data, you would need exponentially many training samples in order to get any non-trivial guarantee to your optimization problem. Does that make sense? Yeah.
It will also be interesting to ask if the function is not actually learnable, let's say within a mononomial level, but it can actually be optimizable.
Well, all these functions are learnable and optimizable. So if you take away the learnability aspect of it, it's not going to make that problem necessarily easier.
This link that you showed before would be interesting to see whether there will be functions that if you really go through this middle step, it's really, really hard, but you can directly optimize it. Is it?
Yes, I agree. I agree. And no, yeah, okay. So I agree. Sorry, I misunderstood your question in the beginning, right? I agree. We look for these. So let me paraphrase. So in addition, like another interesting thing to do would be to sort of say, in kind of like additional question is like to say, well, maybe there are cases in which, what we've shown is that we've shown that in general there are cases, like in general, making decisions from data is generally hard. Okay. But something else that would be interesting to show is that maybe there are cases where kind of like this paradigm of learning and optimization is like hard or doesn't give you, it doesn't give you good results, but a different algorithm that somehow like directly looks at the training data and comes up with a solution gives you like a nice like approximation guarantee. We tried to come up with examples like this, and we were not successful. I'm not saying that there aren't any. I think it's a really interesting problem. But just like we haven't figured it out yet. But I agree, it's a really interesting question. Yeah. Thank you for asking that question. I will pay you at the break. Okay. So let me hold on to give me like 30 seconds. Somebody else want to ask? So the question was, okay, so you showed what you showed, but maybe there is a different learning model. Maybe instead of you're looking at the supervised learning model where you got samples right from some sort of like higher power, right? And now you're trying to like basically come up with a solution. Maybe if you somehow chose a sample yourself in some sort of way, maybe you could do something better, right? And this is exactly what I want to talk about next. Okay, so basically what we have here is we have an impossibility result, and when we have an impossibility result, right, we can kind of like after we kind of go through the 7 steps of 7 stages of mourning, right? We can try to think about like how do we deal with these impossibilities, right? So some of these things we can look at special cases. Maybe like there's some sort of special things that we have about the function, like bounded curvature or community structure. We can look for like easier benchmarks, right? Instead of trying to find like the global optimal solution, maybe I can kind of like construct things that we call like a distributional optimal solution. We can look at like kind of more nuanced learning models, right? If I have like, you know, basically I'm learning things with a lot of parameters, maybe, you know, maybe I can use that. But the last thing I want to talk about is this question here. This is about this learning and optimization in this framework of adaptive sampling that this question was alluding to.
Can I ask another question before you get there?
Yeah.
You know, what about like, you know, there are these Balkan, Blum, Gupta style things that say, you know, when you close the loop on these things, maybe the only instances of problems I care about are ones in which, you know, things which are close in objective value get you close to the same solution.
Mhm.
So what if instead I take your impossibility result and I
Mhm.
think maybe the only functions I care about are ones which, you know, when I take a polynomial
Like
with
these sort of
samples,
stability.
have
Yeah.
stability.
Yeah,
So
these kind of stability. Sure. I mean, that's another, yeah, that's another direction that we explore, but we're not able to produce anything meaningful. But
Because
I
it
agree,
seems
it's
like
really
you just
interesting.
sort of tamper with like a really tiny fraction of the space and then create some like quirks about, you know, where the optimum is
Mhm.
In a way that you just can't observe it from samples, right?
Yeah,
But maybe
The-
those are instances of problems like I wouldn't choose to solve anyways.
the problem, yeah, so that's a good question. The problem with these frameworks, of like the stability frameworks, is oftentimes that they don't, sometimes you can very easily get out of the interesting question because in many cases, right, at least kind of our experience has been like you're watering the problem so much that, you know, you're basically kind of like looking at instances where kind of like anything that you're going to do, you know, it's so easy to get a good kind of approximate to the optimal solution that somehow there's no meat in the problem anymore. Does that make sense? Or we can talk about them more offline, but like, but we haven't been able to add stability as kind of like as a reasonable way to deal with these impossibilities in a way that'll be kind of like, you know, interesting or meaningful. But I'm not saying that there isn't. It just, you know, we haven't found it. So I want to spend 5 minutes talking about adaptive sampling. So we have this impossibility result, right? Where we know we can't observe polynomially many samples and come up with a meaningful solution. Now, why is that, right? Well, if you think about this from kind of like a different language, you can understand that this happens because whenever we're in this sort of situation where we're giving the algorithm this sort of like bag of samples, any algorithm loses adaptivity. What do I mean? I mean that we're now telling the algorithm, these are the only function evaluations that you have, right? And good luck, right? So normally when we have optimization algorithms, what they do is they query for, you know, a certain point, and after they query for that point, then they ask for like a different point, and they kind of like adaptively, right, come up with some sort of solution until they come up with a solution to the problem, right? So what we can then ask is, suppose we were able to do kind of like what you were suggesting, and this would be a way of kind of doing adaptive sampling. So what we would do is we would adaptively sample a polynomial size set of labeled examples in every round, right? So in the first round, we have exactly what we had in our setting. We have a bunch of samples drawn, you know, ID from a distribution. But then we'd be able to, suppose if we were able to look at this, you know, at all these points, and then kind of like in an active sampling way or active learning way, we would then specify, okay, now I'm going to change the distribution that I'm sampling over. And now I'm going to again sample again, and I'll get a different set of labeled points, okay? And then I'll do this in, you know, a few rounds until I come up with my solution, right? So then the question that I'm asking is, how many rounds of adaptive sampling do we need to basically come up with good solutions? To me, good solutions here is a constant factor approximation guarantee, right, to basically optimize submodular functions, right? We know that if we have one round, there is an impossibility result, right? If we think a little bit more about what the greedy algorithm does, then that greedy algorithm basically uses, in the worst case, it uses n rounds until it comes up with a result. But is that what it takes, right? Now, the reason that's also interesting beyond kind of like what we're doing here with like learning and optimization is because if you think about what does it mean that we have the number of rounds, basically is also gives us a bound on the parallel runtime, right? Because if we have in every round, we're basically looking at a polynomial number of samples, you can imagine that we're doing we have like polynomially many machines, we're evaluating like the function on every one of these polynomially many machines, right? And in every round, what we do is we basically kind of using polynomially many machines, right, until we come up with a solution. So, right, what we want to ask is we want to basically ask what is the adaptive complexity of the optimization algorithms that we're interested in. Okay, so I'm going to say that now an algorithm is R adaptive if it makes R sequential rounds, right, of parallel queries. Okay. The greedy algorithm that we saw in the beginning has an optimal approximation guarantee, but it uses K adaptive queries whenever trying to select K like elements to find like the best solution. And the worst case, K is on the order of n. Okay. So here's what we know. We know that the greedy algorithm here, right, basically has adaptivity of, in the worst case, order of n. We know that there's an upper bound and there's a lower bound for that algorithm, right? We showed that with run round, you wouldn't be able to get better than this approximation, right? All the algorithms that we have seen in literature basically were as bad as the greedy in terms of their adaptivity. Okay, all the algorithms, even their MapReduce or whatever algorithm that we've seen, they all had adaptivity in the order of n. So the question is, like, so between like kind of one round with like this terrible approximation guarantee and basically n rounds with this optimal approximation guarantee, right? What's the right answer, right? What is the adaptivity of getting a constant factor approximation for solving some modular optimization?
But you had exponential number of queries as the lower bound, right?
And that's here.
Doesn't that translate to, like, let's say, some polynomial number of rounds?
No, because that means that you have one round of adaptivity.
It's polynomial number of samples.
Exactly, right? That's the model, right? If you were allowed exponentially many, right? Okay, so with Eric Balkansky, so we showed that the adaptive complexity of maximizing this modular function out of cardinality constraint is actually in the order of log n. Okay, so with log n rounds, you can get a 1/3 approximation. Okay. We also showed that you basically can do better with essentially fewer. If you have log n over log n, right, adaptivity, you won't be able to get a log n approximation, right? So it looks something like this. Does that make sense? So now what it says is that it says if you're willing to compromise on approximation, you get like a 1/3 approximation rather than 1 minus 1 over e, but you do it exponentially faster. You do it in log n rounds, right, versus like n rounds, right? And the kind of learning and optimization perspective, it means we need to do adaptive sampling of log n rounds, and then we can come up with a pretty good solution, right, with a 1/3 approximation. Yeah.
If you wanted like the K dependence, would this be like max of or min of K on log n? Or
Yeah. This is all kind of like assuming that K is as large as like n.
K, can you hope to do something sublinear in K?
We strongly conjecture that we cannot do something that's sublinear in K. Okay, so the implication is we have an exponential speedup over a constant factor approximation, and the speedup is optimal. We worked on this and improved this to 1/2, and then together with Aviad and another group, we were able to basically get the 1 minus 1 over e approximation guarantee in log n rounds, so you can get arbitrarily close to the 1 minus 1 over e approximation guarantee and exponentially faster. So you don't even have to lose on the approximation guarantee. Last thing I'll say about that is if you're in the business of some modular maximization, you're probably asking yourself, well, what about matrix constraints? For matrix constraints, you can, a different algorithm and you can get also this optimal 1 minus 1 over e. You can get arbitrarily close to this optimal 1 minus 1 over e approximation guarantee, and you can do this also exponentially faster, but here there's a log n, log k rounds. Okay? Now, just the last thing I'll say is, I'm talking about an exponential acceleration for these optimization algorithms. So what would this exponential acceleration look like in practice? I can tell you if you code up these out, there's been now a pretty long, healthy line of work on these exponentially faster submodular optimization algorithms. They're all terrible, okay? Because they're designed for theoretical, to meet the theoretical bounds, and they're really, I can tell you later what exactly that they do, that they're they're just completely infeasible. But the good news is that you can actually use these design principles and actually design algorithms that have all these nice approximation guarantees, but also work really well in practice. So here I'm just going to show a comparison between this algorithm that we designed called FAST, that is really designed to work well in practice, along with the theoretical guarantees, versus the state of the art, which is the parallelized version of the lazier than lazy greedy. And we took an instance of an influence maximization problem. If you look at this as a function of time, if you look at the objective value of this algorithm, this is what the lazier than lazy greedy algorithm does. Now when you look at these fast algorithm, it does this, right? So it really is, right, deliver on this promise of being faster, right, not only in theory but in practice. So the nice thing is now we with this intuition, we can now go and solve these problems that were difficult to solve previously, and we can really get these speed ups in practice. Okay. All right. So just to conclude, I think that we can all agree that optimization from data is a non-trivial issue that we have to think about quite deeply. Right. Small estimation errors in the objective function can make optimization infeasible. In general, when the input is learned from data, there is no algorithm that will give us some approximation to the optimal solution, even when these problems are learnable or in P or convex. I think that the interesting thing is that in this setting of learning and optimization, it requires us to somehow couple algorithms and machine learning in this in this adaptive sampling way. The algorithms that we're using, they're not the standard greedy algorithms. It requires this new thinking about algorithm design in the setting. So I think it's interesting. And think broader than this, I think that the moral question we should be asking ourselves is, what are the limitations of the optimization models that we're using? And we should understand them and guarantees theoretically, I think before we use them in practice, okay? Because it could lead to pretty poor results. So that's it. So thanks for sticking around.